For part E and F of the problem, we'll be introducing a new notion of convergence, so-called the convergence in mean square sense. We say that xn converges to a number c in mean square if, as we take and go into infinity, the expected value of xn minus c squared goes to 0. To get a sense of what this looks like, let's say we let c equal to the expected value of xn. And let's say the expected value of xn is always the same. So this sequence of random variables has the same mean. Well, if that is true, then mean square convergence simply says the limit of the variance of xn is 0. So as you can imagine, somehow as n becomes big, the variance of xn is very small, so xn is basically highly concentrated around c. And by this I mean the density function for xn. So that's the notion of convergence we'll be working with. Our first task here is to show that the mean square convergence is in some sense stronger than the convergence in probability that we have been working with from part A to part D. That is, if I know that xn converges to some number c in mean square, then this must imply that xn converges to c in probability. And our goal will be to show that for part E. Well, let's start with the definition of convergence in probability. We want to show that for fixed constant epsilon, the probability that xn minus c greater than epsilon essentially goes to 0 as n goes to infinity. To do so, we look at the value of this term. Well, the probability of absolute value xn minus c greater than epsilon is equal to the case if we were to square both sides of the inequality. So that is equal to the probability that xn minus c squared greater than epsilon squared. We can do this because both sides are positive, hence this goes through. Now, to bound this quantity, we'll invoke the Markov's inequality. Which says this probability of xn, some random variable greater than epsilon squared, is less equal to the expected value of the random variable, in this case expected value of x minus c squared divided by the threshold that we're trying to cross. So that is Markov's inequality. Now, since we know xn converges to c in mean square, and by definition mean square, we know this precise expectation right here goes to 0. And therefore, the whole expression goes to 0 as n goes to infinity, because the denominator here is a constant and the numerator here goes to 0. So now we have it. We know that the probability of xn minus c absolute value greater than epsilon goes to 0 as n goes to infinity for all fixed value of epsilons. And this is the definition of convergence in probability. Now that we know if xn converges to c in mean square, it implies that xn converges to c in probability. One might wonder whether the reverse is true. Namely, if we know something converges in probability to a constant, does the same sequence of random variables converge to the same constant in mean square? Well, it turns out that is not quite the case. The notion of convergence in probability is not as strong as a notion of convergence in mean square. Again, to look for a counterexample, we do not have to go further than the yns we have been working with. So here we know that yn converges to 0 in probability. But turns out it does not converge to 0 in mean square. And to see why this is the case, we can take the expected value of yn minus 0 squared and see how that goes. Well, the value of this can be computed easily, which is simply 0 if yn is equal to 0, with probability 1 minus n plus n squared when yn takes the value of n, and this happens with probability 1 over n. The whole expression evaluates to n, which blows up to infinity as n going to infinity. And as a result, the limit n going to infinity of e of yn minus 0 squared is infinity and is not equal to 0. And there we have it. Even though yn converges to 0 in probability, because the variance of yn in some sense is too big, it does not converge in a mean square sense.